Welcome to This Explainer. Today, we're going to totally demystify the underlying mechanics that make modern generative AI models so incredibly fast and scalable. I mean, if you've ever pasted a massive document into an AI and got an instant summary back, you probably felt like it was magic. But it's not magic, right? It is actually a revolutionary shift in software architecture. So let's unpack exactly how that works. So, the big question: how exactly does AI read millions of words in seconds? We're going to explore the hero's journey of data processing here, starting from the absolute slow lane and moving to the massive parallelization we see today. We'll look at the exact mechanism that untied the knot of older, slummish models and basically gave us the blazing fast tools we rely on right now. Let's find out. Here's our quick roadmap for today. We are going to cover the sequential bottleneck, the transformer paradigm shift, decoding multi-head attention, the math behind the speed, and finish up with the real-world AI impact. Let's get right into it. Part 1. The sequential bottleneck. The problem with old AI. Okay, think back to the dark ages of AI architecture, which was really just before 2017. Back then, the dominant way to process language was through recurrent neural networks, or RNNs. The catch with these models is they generate their hidden states one single step at a time. It's kind of like a rigid assembly line. Worker B literally cannot start their job until worker A totally finishes processing the previous word. So if you've got a sentence with 100 words, the model is to process word 1, then word 2, all the way to 100, strictly in sequence. You can imagine how that inherently bottlenecks how much data you can actually process at once. And that sequential bottleneck sharply contrasts with the blazing fast speed of self-attention. With those older RNNs, the processing time scales linearly. 10,000 words? That's 10,000 sequential steps. It's a total traffic jam. But with self-attention mechanisms, it computes everything at once. The number of sequential steps remains basically constant, completely regardless of the text length. All the data gets analyzed simultaneously, a real game changer. Which brings us to part 2, the transformer paradigm shift, a new architecture. You've probably heard of the famous "attention is all you need" paper. Well, this is the architecture that kicked off the revolution, the transformer. The real stars of the show here are the multi-head attention blocks. They completely replace those slow recurrences and convolutions we just talked about. By totally tossing out step-by-step processing and relying purely on these attention layers, researchers created a model that was massively more parallelizable and, frankly, just significantly faster to train. All right, part 3, decoding multi-head attention, parallel processing. Now this is where we zoom into the ultimate weapon that makes this whole engine purr. Instead of relying on a single attention mechanism to compute queries, keys, and values, the researchers had a breakthrough. They figured out that rather than doing this just once with massive, cumbersome dimensions, it was way more efficient to project the data multiple times and run the attention function in parallel. That's the multi-head setup, several attention layers running at the exact same time. Let's break down why this is absolutely crucial. By linearly projecting the inputs, the model actually shrinks the dimension of each individual head. So, for example, it might reduce the dimension from 512 all the way down to 64. And because those dimensions are smaller, the total computational cost stays remarkably similar to just using a single full-dimension head. Think of it like this. Instead of one person trying to read a massive document, it's like a whole team of specialized analysts reading the entire document simultaneously. One's checking grammar, one's checking tone, one's checking facts. It vastly speeds up comprehension without blowing up the computational budget. Part 4. Math behind the speed. Matrix multiplication. Let's look under the hood at the actual math making this possible. The secret sauce here relies on dot product attention, which directly leverages hardware-level matrix multiplication for a massive speed upgrade. Modern GPUs and TPUs are purpose-built to do basically one thing incredibly well: multiply matrices together. By framing the attention mechanism as a series of dot products packed into matrices, the transformer model isn't just clever software, it's software that speaks the native language of supercomputing hardware. But, there's always a catch. As dimensions get larger, those dot products can grow huge. And when that happens, it pushes the network's mathematical functions into a corner where the learning signals become extremely small, essentially freezing or stalling the network. So they introduced a trick, scaling the math by the inverse square root of the dimension. It's a simple but essential tweak that keeps the numbers in a stable range, preventing the stall and letting the model learn continuously and rapidly. And finally, part 5, real-world AI impact. Faster, smarter AI. Let's talk real numbers to see how this technical breakthrough practically impacts the generative AI tools we're using every day. Look at the older GNMT recurrent model compared to the base transformer on an English to German translation task. The transformer drastically drops the training cost. We're talking about floating point operations that are nearly an order of magnitude lower. Yet it still beats the older model's accuracy, jumping from a 24.6 to a 27.3 on the BLU score. Less cost, way faster training, and frankly, much better results. And this foundational speed builds into modern marvels like Google's Gemini, which uses a transformer backbone to natively ingest text, audio, images, and video all at once. Because that multi-head attention mechanism honestly doesn't care if a sequence is a sentence of words or a sequence of video frames, Gemini can interleave all these different modalities completely seamlessly. So how is this implemented at scale today? Well, thanks to the multi-head attention speedup and an optimized variant called multi-query attention, models like Gemini can instantly process variable inputs across a massive 32,000 token context window. Plus, this architecture is perfectly designed to be trained efficiently across massive interconnected superpods of TPUs. Think about it. Trying to process a 32,000 token window sequentially using an old RNN, we'd literally be waiting lifetimes. But with multi-head attention, it happens in the blink of an eye. This processing speed, combined with immense scale, is exactly what allows models like Gemini Ultra to exceed human expert performance across 57 highly complex subjects. It's literally the first model to surpass the human expert baseline on the MMLU standardized testing benchmark. By pairing rapid parallel processing with chain-of-thought prompting, the AI finally has the computational bandwidth to generate multiple reasoning paths and pick the best one without keeping you waiting. So we've seen how escaping the sequential bottleneck through multi-head attention practically changed the world of software overnight. It leaves us with a pretty fascinating thought. As these models continue to scale their multi-headed architecture, what new boundaries of processing speed and multimodal understanding are they going to unlock next? The engine is built, the speed limit is completely shattered. Now it's really just a question of where we drive it. Thanks for joining this explainer.